Examples of conservation of angular momenta. Examples of conservation. Examples of conservation of angular momenta. Angular momenta. Okay. First example. Suppose a person carrying heavy weight in his hand, stretched out, is standing on a rotating platform. Rotating platform. Okay. When the person suddenly folds his arm, his momentum of inertia I decreases. Momentum of inertia I decreases as angular momentum L vector L equal to I omega vector is constant. Okay. Is constant. The angular velocity omega of his body, which is the same as the angular velocity of the rotating platform, increases. Okay. Suppose a person carrying heavy weight in his hands, stretched out, is standing on a rotating platform. When the person suddenly folds his arm, his moment of inertia I decreases. As angular momentum L equal to I omega is constant, the angular velocity omega is body, which is the same as the angular velocity of the rotating platform, increases. Okay. Second example. The angular speed of the inner layer of a tornado is always very high. The angular speed omega of inner layer is always very high of tornado. Okay. In a tornado, air from nearby regions get concentrated in a small space, thereby decreases the moment of inertia I. As angular momentum L equal to I omega constant, omega increases and attains very high values as I decreases. Okay. Second point, the speed of the inner layer. The speed of the inner layer of wire-wide or tornado is always very high. Is always very high. Is always very high. Okay. In a wire wind, air from nearby regions gets concentrated in a small space, thereby decreasing the moment of inertia. I. Okay. as angular momentum L, as angular momentum L equal to I omega vector is constant. Omega increases. If omega increases and attains very high value as I decreases. Okay. Third point. The angular velocity of revolution of the planet around the sun in an elliptic orbit increases when the planet comes closer to the sun and vice versa in order to conserve angular momenta. Okay. Third point. The angular velocity of revolution of a planet. The angular velocity of revolution of a planet, revolution of a planet around the sun in an elliptic, around the sun in an elliptic orbit increases when the planet comes closer to the sun. When the planet closer comes to the sun, okay, comes to the sun, and vice versa, in order to conserve angular momenta, in order to conserve angular momenta, okay, angular momenta. The angular velocity of revolution of a planet around the sun in an elliptic orbit increases when the planet closer comes to the sun, okay, and vice versa, in order to conserve angular momenta. Fourth point. Point number 4, okay, as the motion of the earth around the sun, as the motion of the earth around the sun, okay, as the motion of the earth around the sun is under gravitational force, under gravitational force, which is central force, which is a central force. The angular momentum of the earth, the angular momentum of the earth moving around the sun is conserved. Moving around the sun is conserved. Okay? It's conserved. When the earth is at the perihelion, when the earth is at the perihelion closest to the sun, is at closest to the sun. to the sun, the angular velocity is maximum. The angular velocity is maximum. Angular velocity is maximum, and when the earth is at the aphelion, and when the earth is at the aphelion, aphelion is that farthest away from the sun, is that farthest away from the sun, its angular velocity is minimum. Its angular velocity is minimum. Okay, minimum. As the motion of the earth around the sun is under gravitational force, which is a central force, the angular momentum of the earth moving around the sun is conserved. When the earth is at the perihelion closest to the sun, the angular velocity is maximum. And when the earth is at the aphelion, that means farthest away from the sun, its angular velocity is minimum. Fifth point, okay? Fifth point. During the course of the performance, an ice skater, ballet dancer, takes advantage of the principle of conservation of angular momentum by stretching out its arm and legs and vice versa. Okay? And during so the momentum of inertia increases, I decreases, hence angular velocity decreases and I increases. Fifth one, the shape of galaxy. Sixth point. The shape of galaxy. The shape of galaxy. Okay? The shape of galaxy. Galaxies are physical systems. Galaxies are physical systems. Galaxies are physical system. Galaxies are physical system. Galaxies are physical system. Okay, containing anything from 10 degree to containing anything containing 10 to the power 9 to 10 to the power 12 stars with a lot of free gas. Free gas, okay? Bound by gravitational attraction. Bound by gravitational attraction. Okay? Bound by gravitational attraction and free to rotate about their own axis and free to rotate about their own axis. Okay, of symmetry. Axis of symmetry. Okay. The contraction of the gas in a galaxy. The contraction the contraction of a gas in a galaxy, in a galaxy, in a galaxy, the contraction of a gas in a galaxy continues in order to conserve, continues in order to conserve, in order to conserve, in order to conserve its angular momentum, its angular momentum, okay, angular momentum, okay, until equilibrium is attained, until equilibrium, until equilibrium is attained when the inward pull due to gravitational, the inward pull due to gravitational force on it just balanced by the outward pull due to centrifugal force, centrifugal force. This is capital G, capital M, small m upon R square equal to mv square upon R. Okay? The shape of galaxies are physical system containing anything 10 to the power 9 to 10 to the power 12 stars. Okay? With a lot of free gas bound by gravitational attraction and free to rotate about their own axis of symmetry. The contraction of a gas in a galaxy continues in order to conserve its angular momentum until equilibrium is attained when the inward pull due to gravitational force until just balanced by the outward pull due to the centrifugal force. Capital G M upon R square equal to mv square upon R square. Okay, thank you.